goes there. In the back of the column of the bridge, you have turbulences, tourbillons. Vortices. And I'm quoting Leray. Can one predict these ondoyantes, roundy shapes, or should we renounce to this prediction and just create a stochastic modelization? So he attacks the question of turbulence. So you can say that it starts from a concrete problem, but you will see that concrete and non-concrete are going to be mixed, and just like the water in the river. He attacks the question of turbulence with the key remark that existence of solution can happen without unicity. He develops his ideas and introduces a new notion, the notion of weak solution. I will not go into the detail, but just know that it's a key idea that will have a strong future because it will be later at the heart of generalized functions of Sobolev. Weak solution. He calls them turbulent. So the same notion which for him is connected with some physical, mechanical problem, he translates into a pure mathematical notion, weak solution, because it can be defined in 2 lines. And all this is inspired by his meditation looking around the bridges on the River Seine. At that time, specialists of fluid mechanics wonder of the physical meanings of solution that can become infinite, because this weak solution can become infinite at some points. So I would like, could you help me to push down? No, not yet, so I want to stop this. I want to show it in a few minutes. Sorry. Can you close it? Okay. Thank you, sorry. During the winter 1932-1933, Leray visits Berlin under a Rockefeller Fellowship with Schmidt, famous mathematician, and Richard von Mises, famous probabilist. About to leave, it's 32-33, the Reichstag is burning, and Hitler is becoming chancellor. He meets Liechtenstein, the man I was mentioning. Liechtenstein at that time was not an engineer anymore, he was professor in Leipzig, where he was trying to introduce topological ideas in dynamics. Liechtenstein insists that Leray should read the publication of a young Polish mathematician from Lvov, Julius Schauder, member of a group of mathematicians in Lvov, who were creating under the direction of Stefan Banach a strong school of mathematics specialized in functional analysis. I have seen by chance today a paper announcing a talk by my friend Tikhomirov about the anniversary of Banach. So I regret I will speak to Tikhomirov about it. So Banach was a great mathematician, and Julius Schauder was involved working with Banach. And this is the beginning of a long and deep friendship with this Julius Schauder, and a productive collaboration between Leray and Schauder, a beautiful and pathetic story which will end under tragic circumstances. And that's why, of course, it's one of the reasons why I've been working on Leray and Schauder. It's because, you see, there's documents, and later Leray passes his thesis, Schauder joins Leray in Paris, they have lunch in a small restaurant Rue Soufflot, and in the afternoon, walking in the Luxembourg Garden, Leray explains to Schauder that because of his results of Schauder in Lvov and of his own Leray's result, Leray can prove the existence of solution independently of the whole question of uniqueness. In general, all the classical physics says that you have solution, when you want to describe some phenomenon, then you have some partial differential equation, and to be sure, you have some kind of Cauchy principle, you have data, even given the data, then you have existence and uniqueness. But Leray has found that with the methods they have and the result of Schauder, he can prove existence without uniqueness, without wondering about uniqueness, and it makes things possible which were not possible before. And Schauder replies to this remark in the Jardin du Luxembourg. He replies to Leray, unfortunately I don't speak German, das wäre ein Satz. It would be a theorem. And of course it becomes a real strong theorem, which he was right, which is known later on. It's a famous paper, Topologie Équation Fonctionnelle. The theorem of Leray-Schauder is a fixed point theorem in infinite dimensions, so I don't go into details. I would not have gone into details even if I was with my colleagues of the Arnold seminar, so don't feel sorry. Then Schauder goes back to Lvov. The letters sent from Schauder to Leray from 1933 to 1938 constitute a unique document mixing personal emotions and mathematical life. In his article After the War, Leray tells in details the story of his friendship with Schauder and gives a short analysis of these important documents. Now, what happened is that we have found this document recently in the archives of the library of my university. I had a copy of them, a photocopy, which I didn't know where I had got, and it was not very readable. And we found the original. So we, of course, not. You will understand why, not the letters from Leray to Schauder in Poland, because Poland soon became under control of the Nazi, but all the letters from Leray, from Schauder to Leray, from 33 to 38. And I hope we will soon translate and publish them. In 1935, Schauder, so please tell me what to do. I'm sorry to make you move. Schauder participates. Yes, the one, yeah. So participate. So in the documents we have found there is this photo, but this photo was already published in some books. It's an important event in the history of mathematics. It's in Moscow. As you can see, here it's written Grupa Pierwoj Międzynarodnej Topologicznej Konferencji Moskwa, Septembra 1935. I have a copy here. I'm not sure. 35. I'm not sure if it's written. Congrès de topologie.
Congrès de topologie tam napisane.
Yeah, but it's not written who made the photo. Anyway.
Kuratowskie.
No, the names that are here are the name of the people here. So I should tell you who they are. At least some of them, because it's really amazing, the meeting there. It's the first international meeting on topology. So it's really the beginning of a international status for topology. Where's my photo? Yes. So from left to right, so below, you see Kuratowski. I have the list in the back here. So standing, so in the back. Okay, the young man who looks nice in the back, the second from the left, is Hassler Whitney. The first is Czech. These two are famous. I will just mention the fifth one is Lefschetz, who became a very famous topologist. And I think that already there, the accident had happened. He was an engineer, so talking about pure and applied mathematics, he was an engineer, and he got working in a factory. He got his two arms cut, so he decided to go to topology. Lefschetz with a mustache. Then the man, strange looking, is Freudenthal, also well known. Borsuk, I don't care too much. And the last is Tikhonov. The last in the back is Tikhonov. And in the front, Kuratowski, Schauder, nice looking, handsome man whom I was talking about. Convorson, he got very famous. And then Alexander, whom you might know the name of, and Hopf, and then Alexandrov. So Alexandrov is here. For those of you who have read my book with Lauren Graham, this is Alexandrov. This one I don't know. Anyway,
The lady,
huh?
there is one lady, and it's really...
Oh yeah, the lady I get from her name, Rozhavska, but she's not, her name did not remain. Okay, so this Congress was very important for various reasons. It's inside, if I try to restrict inside our story, then without getting into details, some topics were discussed, were really in fashion at that time, and were discussed at this Congress, and some strange things. So I'm writing, I've wrote here that Whitney will later give a vivid account of the event. So it was very vivid and active, and lots of things were happening. In particular, André Weil, the famous French mathematician, who is not on the photo, by the way, got to know and became very friendly with Alexandrov.
Probably he was a photographer.
Maybe. Among the topics discussed, there were central topics that were proposed by various people. For example, I don't want to go into detail, but there's a notion of homology. And in the last couple of years before, at least two persons had the idea of replacing homology by taking cohomology, by dualizing this notion. I don't want to go into detail, it's not that important. And the two persons were de Rham, who is not in the Congress, and Alexander. And then at the Congress, at least two people gave talks, two different other people gave talks with the same idea. So four people in a few years had the same idea. So it seems to be that it was a kind of a natural idea, but this idea is very important, and we will show in a minute, I will show you what was the effect. Schauder was there, and one can say that one of the signs of a good mathematician is a quick mind. Schauder saw quickly that this notion was important, and in his correspondence we can see that he transmitted to Leray that this thing that had happened, it was useful to Leray. So now, suddenly, 1938, 3 years later, the war breaks all activities and kills all projects. Leray goes to war as an officer and is imprisoned in a camp for officers in Edelbach with 5,000 prisoners. And could you please show me what to do, and I can do it myself.
Yeah.
Okay, let's see. So this is, okay, so this is, on the left you have the list of the people in this photo, and on the right you have Leray discussing with Schauder in the garden in Paris. Original photo. So I push, oh here I push. And now, that's it. This is the photo, so again. Yes. So here is Leray, and here Leray was taken in a camp for prisoners, but officers, he was an officer. So this is a photo taken while Leray was in captivity, and he decided to create a university in captivity. It was not a gulag, it was not a camp where people were dying. It was camp for officers of the French army in Austria. And he decides to create a university of captivity. So here is Leray, prisoner of war before the war, and here in the middle it's Leray. And let me see if I can do it.
No.
Okay, so this is, he decides it, so he teaches, and he starts again his research of mathematics on turbulence, and he sends even notes. This is May 42, he sent notes to the French Academy. And then something important for the history of mathematics happens. He changes subjects. He doesn't want to work on turbulence because he's afraid that the applied mathematics he's doing might be useful for the Germans. So he switches. So he writes about his switching from turbulence to pure mathematics in the following way. Était-il raisonnable de faire des recherches en topologie algébrique? Sorry, I will translate. Was it reasonable to do research in algebraic topology? During my 5 years, I was prisoner in Nazi Germany from 1940 to 1945, imitating Poncelet. You know probably that Poncelet was a prisoner of you Russians on the Napoleon War. During 5 years, and Poncelet made very important progress to geometry while he was a prisoner by the Russians. In this isolation, in this big scientific isolation, I had enough original ideas so that they could contribute to the renewal of algebraic topology. That's Leray writing. So he decides to go back to abstract mathematics, but meanwhile he's still thinking of his work for which he has been working very hard with Schauder. The proof needed to pass by approximation from finite dimension to the infinite dimensional case, and Leray was hoping to find a different approach. So in fact, contrary to what has been told afterwards, he tried to make progress on his previous work in applied mathematics, but under the appearance of very abstract things. And this succeeded in creating, with the help of this trick that Schauder had mentioned to him, to the creation of a new theory that he called, when he came back at the beginning, he called it cohomology with variable coefficients. But in fact, it was a new theory which had very big developments, theory of sheaves. It's called theory of sheaves. And what happened was that later on, when he came back, this theory, another result from him, gave him a position at Collège de France in